All right, we are going to go ahead and get started. I need some volunteers over here. All right, catch. Think fast. One more. I see, just like, no, not me. All right, whoever has your magic markers, please. I would like for you to come to the board and please draw me. You can each have your own interpretation. Best fit line for these set of points here. So please come on up, however you would like. All right, we got one line over here. Go ahead. Okay, we got a different line. Awesome. And we have a third line. Great. Okay. All right, so in this class, we are going to be essentially doing these things, right? So drawing sort of lines of best fit, but really the idea is to understand kind of the relationship between sort of X and Y. And we have a couple, there's a couple different ways we can go about doing this. Sort of going by people's guts, we have a couple different lines showing these best fits. All right, so who thinks we're not gonna shame anyone here, but see, raise your hand if you like the green line best. Sorry. How about the red line? Okay, wow, okay. A lot of people. What about the blue line? Smaller number, but most people like the red line. Okay. So why is it that we like the red line the most? Is there something you feel drawn to it? Yes.
It's linear and it goes through an area where
Okay. All right, so let's unpack that. So it's linear and it goes through a lot of where a lot of the other points are. So, okay. So I'll talk about your first statement a little bit later, but okay, going through places where a lot of the points are, is there some way we can like do that in an objective way? Yes. Yeah, exactly. So if we look, okay, let's look at the red line. If you measure the distance each point is from the red line, right? We can compare that against, say, the distance each point is from the green line. And I can say that if the distance between the line that I drew and the points, if you like add up all of those distances and it's the smallest, then maybe that's the best fit line, right? Is that kind of what we're thinking here? All right. Okay, so let me go by that metric, which is to reduce the distance between my line and each of these points. All right, I'm gonna beat the snot out of all of your guys' points here, or all of your lines. Ready? All right, sweet. Okay, so this line is a better fit than all of your guys' lines according to that definition, right? And in fact, so is this one. And so on and so forth. So I think one of the big things that you have to remember here is that we're going to come up with lots and lots of different ways to think about how you can interpret these fits and different techniques of doing these things. And kind of no matter what you do, it's going to be driven by some of the assumptions that you're making about the data. And so one of them being, right, crucially, maybe that red line is the best fit if, right, if we assume that the sort of functional form of these points and the relationship between x and y is linear. But if it's not, you might be doing stuff like this. And then how can we tell whether, you know, the first purple line I drew is better or worse than the second purple line that I drew, right? And they might be sort of extreme examples. So does anyone already know kind of one of the issues with drawing your purple lines like this? Yes.
I mean, that doesn't tell us anything.
Well, I mean, why not? It tells you something.
It doesn't tell us anything practical.
Okay, why not?
We can't. We could say that there is a very strongly oscillating relationship between x and y, but when we look at the data itself, we can see that there isn't. There's two outliers and a generally positive correlation.
Yeah, so we're going to put that intuition into sort of practice. I think what you're getting at, so practically speaking, you can look at that and say, oh, that's nonsense, right? But you might be working in many dimensions where it can get really hard to visualize something like this. So we need to be able to have like real quantitative diagnostic measures. So the term I think you're looking for is called overfitting, which means that this, right, it fits the data perfectly, but say you leave out some data and then you put it back in to see how well it does, right? It's going to do a really poor job of estimating because maybe I have like an X right here and you can see these lines are nowhere close. And in fact, if I put an X right here, the distance to the line is very, very far away. Okay, so these are the kinds of issues we'll be thinking about and dealing with. But let's revert back to our initial guy. And let's build off of what you guys were saying for your intuition here. So if I have these sets of points, and we'll be working primarily in the sort of linear space to begin with. And we'll start to sort of gradually move away from that as the course moves on. So going back to this idea of coming up with an objective measure for how good any particular sort of fit is. So the objective measure for the best linear fit is using essentially this exact technique. And so I'm going to look at my distances from here. However, if I were to do the distance from X to my line, what happens to the measurement of the distance below versus above the line? Yeah, they're going to cancel out, right? Because you have negative values here. Okay, so the way this is done is called ordinary least squares. Okay, and so what you do is you actually square these distances. And so this is a type of regression which describes the regression is just a sort of generic term for techniques that we're going to be doing to describe the relationship between my explanatory variables, which we'll be usually denoting as X in this class, and your response variables, which you'll be denoting as Y. So we square these, right, to deal with this issue of the below and above. Is that the only way that you can get rid of these negatives? How else might you do it? Yes, I saw it. I saw you. All right, absolute values, exactly. Does anyone know why we do squares instead of absolute values? So OLS, which is this thing, has actually been around for quite a few decades. And way back when you are computing things like the slope of this line, we didn't have these sort of high power computers back then. And so it turns out to do an analytical solution of this technique, squaring is a lot easier to solve than doing an absolute value. And so that's since sort of held on over time. You can do ordinary least absolute value regression. That is a thing, and it's a lot easier with computers nowadays. But just know that's essentially the sort of reasoning behind using this particular technique. Okay, so let me describe the characteristics of this, what we're going to call regression. So y is equal to beta x. We'll have a plus alpha and then plus epsilon. And I'm going to have a little I for each of these. Okay, so if you remember from high school, you have this, I think it's mx plus b. Is that something like that, right? So who can tell me what this beta represents? The slope. Yeah, that's right. And this alpha represents the intercept. Yep. So this is your beta slope. And this here would be your alpha equals intercept. Okay. What are these little i's and why do we have this epsilon I over here? So each I represents an individual data point, okay? So each of these i's represents an individual x here. And this term is known as your random error term, okay? And so this describes the noise that would push these x's away from the line, okay? And so let's use a different color here. This term, you have a separate epsilon I term, which represents this distance for every single point. And so if I wanted to find the exact point of my x, I would do this equation where I would find this here, which beta x plus alpha, which would tell you the point on the line. And then it gets displaced by your error term here to meet the actual value. There's a different equation that you guys might see, which looks something like this. Y hat equals beta x plus alpha. And these hat terms mean these are your predicted values, okay? So these are the terms that come from your model. And so the y isn't the actual one sort of representing the x, it's representing the point that you predict on the line. So that's the sort of difference between having these hat terms versus not having them. Any questions about that? Okay. So how do we go about calculating our betas? Okay, you can imagine, right? Essentially what we're doing here is maybe I'm drawing a couple different lines. Like so. And essentially, you want to go through some kind of procedure where I figure out which beta and alpha combination will give me the sort of smallest least squares of my errors, right? So essentially, if we're thinking about this in terms of an optimization, we want to be doing something like minimize the sum for all of my data points, the error squared, okay? So we want to find the line that will do this the best. And there's two ways to do this. And this is kind of generally true for any optimization. So numerical methods, and you have analytical methods. Okay. So this means you can do it basically, you take the equations and you solve the equations. So you can't do that for all optimizations, but for OLS, actually, it's been solved for quite a while. And so this is, I'm going to coin this kind of like a solved optimization. And we aren't going to get into kind of the theory behind this, right? So this is the type of thing that you would learn in like a basic like intro to regression class in like a statistics or in an econometrics class. So the beta hat is equal to xtx inverse times xty. And so these are, if your data are kind of arranged in matrices, x transpose times x inverse multiplied by the product of your x transpose times y. So what I'll say about this is that in this class, when you go into R and you run it like a linear regression, most of the time it's going to be doing something like this in order to solve for your betas. Okay, and so you, again, this in a more sort of theoretical class, they would show you kind of how to derive this. And you might do these kind of by hand for a little bit, but we're not doing that. We're applied. So the other one on the numerical side uses a technique called gradient descent. So this is something that you might have heard of if you've ever taken kind of an optimization class. And so whereas this, you just take your data and you solve for your beta, this is much more in line with that, what I'm kind of describing here. You can think of it as like a intelligent way of guessing and checking. But every time you guess, you're moving in a sort of better direction. And the way they do this is with doing sort of derivatives and sort of following following this sort of gradient down to get the best values for beta. So this is solve for beta iteratively by guessing and checking. Okay, so why the heck would we ever do this if we could just solve for the betas? So it turns out actually that this gradient descent method ends up becoming the preferred method once you get to really sort of big data sets. So the issue with this is to do the inverse of a matrices. If you have a really large data set, lots of variables, lots of rows, this becomes extremely memory intensive. Okay. And that can even kind of loading in your data into matrices of this form can be can even become sort of computationally intractable once you're at a certain size. Whereas gradient descent is a very efficient method that can work very quickly to solve for your betas. And so there is a point at which it actually becomes somewhat preferable to use gradient descent. It's not too often in like this class where you would particularly use this unless your sort of project demands like a very large data set. So most of the time you'll still be kind of doing this side of things. But if you are running a linear regression, which is traditionally something that gets solved very quickly and it's taking a really, really long time, you might want to consider looking into doing it with gradient descent instead. Okay. Any questions about that? Okay, so let me move over here. The next thing we'll talk about is our standard errors. So let me draw this again. Oh, the camera's very unfocused. I would not rely on attending and watching the YouTube videos, I guess. Okay, so here we have a line going through these points. And consider that in a linear regression, right, you are fitting to some sort of set of points here. And let's consider an alternative set of points. Let me actually just do that with different color. The erasers are over there. All right, let me. All right, so this might be my best fit line for these guys. And let's take the same set of points and I'm going to just spread them out to be sort of farther apart. So it might look something like this. So this might be here, this might be here. This one looks a little farther. And say here. Okay. So I'm trying to make them sort of equidistant so that my red line kind of also fits in the same way. Let's suppose these are both your linear regression lines for my black points and then the corresponding red points. Okay. So even though the points are in different sort of locations, my lines are kind of in the same place, right? Which line do you guys think is, let's say, more certain? Raise your hand if you think it's the black line. Okay, versus the red line. Yeah, okay, great. And so the kind of intuition, right, is that even though the line looks the same, they're kind of closer to the black points. And so let's suppose now that I wanted to kind of introduce another point there versus there, right? You can imagine that the black line is going to shift a little bit. It's going to shift less than the red line would shift to kind of accommodate that new point. Okay, and so actually when we talk about these lines, we have inherent uncertainty about the slope, right? So there's, in reality, you've got some beta, but then that's kind of plus or minus something called a standard error. Okay, and so that kind of says essentially that, hey, I made this estimation, but I might be wrong. And in reality, the slope might be somewhere in between some set of other values of beta. And for the red line, that set of uncertainty might be a little bit bigger to accommodate the fact that the points are sort of farther apart. Okay, and so this term is known as the standard error, which I just kind of just described here. And so this you might see more traditionally as this symbol, sigma, right? Totally blanking. So sigma of beta. And I'll give you the equation for this in a similar manner as I was kind of giving you, how you solve for beta. But again, this is something that that the computer will kind of just tell you, right? We just want to make sure we understand what that term means. Okay, so this is the sum of yi minus yi hat squared divided by n minus 2. And all of this divided by sum of xi minus x squared. Okay, and so, right, your yi is the actual point, the yi hat square, or the yi hat is the point on the line. So this term here this is actually the sum of your squared error. So that's exactly that thing over there. So epsilon I squared is equal to yi minus yi hat squared. And so what is this describing? This is describing a distribution of values for your beta, okay? So this beta is one number, this exact line, and the sigma describes a normal distribution of that one point. So if we say that this is beta that we've estimated from our fit, like I was saying, we actually have some uncertainty about that point. And the uncertainty around that particular coefficient is represented via this very poorly drawn normal distribution. And this means that, right, if you are beta plus sigma, beta plus 2 sigma, beta minus sigma, beta minus 2 sigma. So this means, right, in a normal distribution, this is defined as 68% of the points are within here, and then 95% of the points are within here. All right. Hopefully this is somewhat of a review, but if this is confusing to anyone, please speak up now.
I just can't do why.
Oh, sorry. So okay. Yeah, this is beta here, beta plus sigma, beta plus 2 sigma. So it's describing, right, just like a normal distribution. So effectively what that means is I can alter my beta like some amount, right? Because I'm not quite certain what the slope is going to be. And I can go from one slope to another slope and say that with like 95% of the time, right, we'd be confident that it looks something like it's within that sort of range of betas. Yeah. So that's that's more of actually a philosophical question. It's like when. Okay, actually, let me address that this way. So there's this kind of question of actually, I'm going to do it over here. Okay, so we're going to have some points that look like this. So let me use a different color. Okay, if you have a slope of 0, what would we say about the relationship between x and y? I see people doing this. Yeah, so x and y would not be related, right? There's no, as x changes, we wouldn't expect y to change necessarily in any way. So they're independent, right? There's no sort of correlation there. And so when we say that, right, there's no relationship, there's no effect, my beta would be 0. Okay, and so sort of getting back to your question, I think the idea is kind of like, okay, if I have some kind of relationship, but you have some uncertainty about what that line actually looks like. So maybe it could be that, but it could also be maybe flat some of the time. This is one of the big questions that we talk about when we say something like, oh, there's a statistically significant effect, And all that means is that within that range of uncertainty, we want to be able to say that beta is greater than 0, okay? Which means that there is some effect, there is some relationship between x and y. Let's say, according to our sort of distribution, right? Let's say that half of the time there's no relationship, or the relationship is actually negative. What would you guys say? Would we trust any inference about the beta number that we came up with? No, you're saying no. Why is that?
I think if we understand that there's not supposed to be any, and we are getting a result that should shine some concern on our methods.
Yeah, well, it might not be on our methods. It might just be that there's not really a relationship, okay? Okay, I guess what I'm trying to say is some of the time you might have a line that looks like this, but maybe the uncertainty goes like really, really big. And so some of the time you might have a 0 effect versus something with a standard error that might describe a relationship that looks like this. And you would say, you know, this is a distribution, so this will go out to infinity, and it could, in theory, become 0, but maybe the chances of that happening are like 1 in a quadrillion, okay? Versus with the first line that I drew, with the first set of uncertainty, you know, if your standard errors are really big, the chances of your line being 0 might be, say, like 30% of the time there's no effect, right? And so when we talk about statistical significance, which is related to this idea of your standard error, it's kind of an arbitrary thing, right? People decide, okay, as long as the effect is not 0, or sort of the opposite side, 10% of the time, then we're okay with that answer. So that's like at a 10% statistical significance. If you say, oh, it's not 0, you know, 95% of the time, right? Only 5% of the time would it flip, then that's statistical significance at the 5% level, and so on and so forth. Does that kind of answer your question? Somehow, okay. Well, if you want to clarify your question now, that I'm happy to try and answer.
Because you are trying to find
Yes.
sensing like it could not be exactly this one, right? So
Yep.
as like people draw 3 lines, right? So anybody can guess whatever. So as our computer is doing, guessing the line. So how to know that this line, how we can see that yeah, this line is the best way.
Oh, okay. Okay, that's actually okay. So that is slightly different. So that is having to do with the original estimation, right? So that you can kind of figure out empirically, because I can measure all those distances, right? As I was saying, all those errors.
So that's why I was thinking that you are measuring all those distances.
Yeah, yes.
So they can, like, give us some estimation there.
Yes, exactly. That's actually what this does. This thing is a solution to that question. Basically, there's a bunch of different slopes I could have. Though if you calculate the slope in this way, you will calculate the smallest slope, guaranteed. It's a sort of there's like mathematical rigor going behind why that's the best one. It's the main problem is that even if it's the best one, sort of reducing the distances here, there's still what we would kind of describe some uncertainty, especially like, suppose you took a point away or you added another point, right? That like perturbs the line a little bit. And you can think of the standard error as like in this example, if I took a red point away versus a black point away, the degree to which my line shifts is kind of a analogy for this standard error thing, which is kind of describing how certain you are that this slope is kind of representing the best one. Yeah.
Clarify that if you have a lower standard error,
Yes.
then if you like the black points, like if you take one of the black points out,
Yeah.
like, is your beta going to differ a lot more?
No, it'll differ less, right? So the standard error, right, is basically the smaller the standard error is, the more certain you are that this is your right slope. And so like the kind of wiggle of your slope is smaller with a decreased standard error. And if your standard error is really big, that's basically saying, oh, I'm actually not too sure about this slope. And so maybe the slope looks like this instead of like this. Does that make sense? Yeah. Okay. Any other questions about the standard error? This is, right, this is one of the sort of most common things that people talk about when they're kind of showing their regression results, right? This is like a canonical way of people saying, oh, my regression is statistically significant to the 5% level, blah, blah, blah. That's what this is referring to. And I think one of the things that, one of the things to keep in mind is that I think, unfortunately, a lot of people commonly kind of equate the like goodness of your model, like how good my model is, to this idea that you have demonstrated like statistical significance, right? People will say, oh, I have this model that has statistical significance at the 0.1% level. It's so amazing, right? Okay, that might be amazing, but you should have in your mind like very clearly what that means. It's not telling you how good the model is. It's just telling you that it's quite likely that the slope is kind of what they're describing and that there is an effect, okay? And that's all that means. Okay. Yeah. So, yeah, statistical significance basically says at a specific sort of percentage level, as described by that sort of normal distribution, some percent of the time, your slope may fall to 0 or below or whatever. If your coefficient is positive, it's 0 or negative. If your coefficient is negative, then it's 0 or positive. So the percent of the time, so when you wiggle your slope, it's like this, if my slope looks like this, and then 50% of the time it looks like this or below, and then let's say 90% of the time it's 0 or below, that's kind of what they're describing in terms of percentages for statistical significance. Okay. The other common one that you will hear as a sort of measure of how good my model is something called an R-squared. So this is equal to, this is known as the coefficients of determination. So this describes how much variation is captured in the model. Okay, and so the equation for this, again, this is something that I'll put as your reference, but this is right calculated by the computer. 1 minus the sum of yi minus yi hat squared divided by the sum of yi minus. Okay, here's the equation. What the heck does that mean? So I think the best analogy for this is I forget how many times I have to make these plots in this class. Okay, so we've got our thing here. So the R squared is basically saying something like, okay, I've seen that you are fitting this kind of line here. How does that compare to if I just took the average of all the y's? Like that. So if you just average your y, this is y hat here. So in the dotted line, you take the distances, right? And you sum them up squared. And then you can do the same thing against the average of y, and you compare them, right? And so, okay, if this number is really small, that means that your dotted line is really close to your x's, okay? If this number is really big, that means your x's are really far from your line here. So if this is close to 0, divided by this sort of big number, you're getting a really small number here, right? And so it'd be 1 minus a really small number, so it gets close to 1. So your R squared is going to vary between 0 and 1, right? Because the other way around is, let's suppose that there isn't much difference between this flat line and your dotted line. Let's say your dotted line actually looks something like this, right? But then let's suppose that the distances are really large. So this term will get closer and closer to 1, which makes R squared 0. Okay. So again, this is how much variation is being sort of captured by your model on average. This is another common one that I would say the two biggest ones that people kind of lean on, right? Statistical significance and R squared values. And they say, my model's like amazing. It has an R squared of like 0.95. It's really close to 1. Okay, great. That means that, right, you've captured a lot of the variation, but that is just one more sort of diagnostic tool for measuring, I guess, how good a model is. And we're going to talk about other sort of metrics of measuring and diagnostic tools for measuring the quality of your model. So just know that when someone says they have an amazing model because their R squared is really high, okay, great, that means something, right? We don't kind of just say R squareds aren't important, but there are a whole bunch of other sort of diagnostic tools that we're gonna look at to kind of demonstrate why or other ways of looking at how good a model is. Okay, any questions about R squared? Okay, let us now go into our studio and look at some of this in practice. So while this is going, let me pull some things up. Okay. So let's look at how we can implement some of this stuff in practice. Okay, so what I'm doing here, I'm using a new function. I believe we haven't seen this before. This is RUnif, which stands for random uniform distribution. Okay, so this is just drawing from a uniform distribution. The default values are 0 to 1, or between 0 to 1. So what we should see, and everyone's going to have different numbers here, but if I type X in my console, I should have a vector of 20 numbers randomly between 0 and 1. Great, and so we can see that's happening here, right? 20 numbers between 0 and 1. So what I'm going to do is actually construct a sort of very artificial regression. So I'm going to have actually, I'm going to call this error. This is my random error term, which I'm going to draw from a normal distribution between 0 and 0.1. So I run that. So R norm stands for random normal distribution. I draw 20 times and I have a mean of 0 and a standard deviation of 0.1. Okay. And we are going to construct this. Oops. Okay, so we've constructed a set of y's based off of this relationship. So this is the real relationship. Usually, right, you would get the x's and you get the y's, but you don't get the 0.5 and the error term, okay? But we get to kind of, we get to play kind of this all-knowing character and have sort of omniscience about what the real relationship between x and y is in this case. Okay, so we know the true value of beta, which is 0.5. Yes? Oh, I made it up. Yeah. I am taking a bunch of x's. I am making a relationship to y and perturbing it in this way. So I can plot my x's and y's. So this is using the base version, which hopefully we'll get away from if we have a little bit of time today. But I'll just do this for now. Okay, so mine looks something like this. Yours might look a little bit different. But when you plot something, it'll also show up here in the bottom right-hand side. And so these are my x's and these are my y's, and I want to maybe fit some line through these points. Okay, and we're going to see how well our regression does to try and estimate what we know is the true relationship, which is this 0.5, but that the regression isn't going to know in sort of any way. We're just going to give it our x's and our y's and see if it can figure it out. Yes.
The points one, the
Yes. So our norm 20, 0.1. So 20 is the number of times we draw from it. 0 is the mean, and 0.1 is the standard deviation. Yeah. So a normal distribution is described by two parameters. It is described by the mean and is described by the standard deviation. And with those two, you can perfectly kind of describe the characteristics of a normal distribution, right? This would be analogous to like if you had a uniform distribution, also needs two parameters, which would be the min and the max, right? So different distributions require information about different sets of parameters. Okay, so model.fit lm y squiggly x. Okay, so this is how we run a regression in R. So LM stands for linear model, okay, and then you have y, is that tilde x? So this is saying you put your response variable on the left-hand side and your explanatory variable on the right-hand side. Okay. Actually, I'm gonna do this slightly differently. So commonly you'll actually see it like this. Where's my mouse? Okay. So we'll have for model.1. Oops. So here, I'm just making a data frame of my x's and y's, so we can see what that looks like. It's just this table that lines up my x's and my y's. And the reason why I'm doing this is I just want to show, usually, right, when you have a data set, you'll be working in a table, and the way that you reference is like this. So you can feed in direct vectors of the y and x's, but here I'm just showing that you can call in column names from a like data frame in the LM function. Okay, so I'm going to run this, and what do we see here? Summary of model.fit. Okay. Okay, I'm actually going to, I'm gonna shrink the font just, actually, no, we'll just make this window bigger. One sec. Okay, let's try that again. Okay. Wait, if I do. Here we go. So when you type summary of this thing, this is what you'll see. So this was my formula. So the way the nomenclature works is we say we regressed y on x. Okay. So residuals are the error term. So this is the yi minus yi hat. And so we can see the distribution of the residuals here. We'll talk a little bit more about residuals in I think the next class. And then here we can see our estimates. Okay, so what is the true value of alpha? No, not quite. What was our equation? Our original equation to determine y. So this is the one that we are omniscient about, that you normally wouldn't know. So it is this guy up here. Okay, so the alpha is actually 0. There's no intercept. So we would expect the intercept value to be 0, and then we are hoping to get a value of 0.5 for my beta. So here we have an estimate of negative 0.03215. So pretty close to 0. And in fact, so this is saying that it will intercept a little bit below 0, but like I said, there's some uncertainty about that coefficient value of 0.04114. So you can actually see that even within the first standard error, it would go to 0, right? It goes up by that much or down by that much. So something like, a little less than half the time, this would be 0. Okay. We have an estimate of 0.59 for our coefficient here. And we know that the true value is 0.5. And so did it do very well? Well, it's also saying, well, I'm not entirely sure that it is 0.59. There is some standard error about that. And so to what we know is the true value is that it would be 1 and like 1.2 times the standard error to get to 0-ish, right? Something like that. So that means, I mean, you can look this up in a table, but some percent of the time, we know, let's say that's probably going to be around like 30% or so of the time we know that it's going to be sort of reach the sort of actual value. So it's close. So then the statistical significance, right? What are these guys saying? So here, this is saying my t-value and my probability. So let's just figure out what this means. So within 0.78 of a standard error, we would say that the value of the intercept is 0, which means that 44.5% of the time, the slope, or sorry, not the slope, the value of my alpha would be 0. Compared to x here, okay, you would need to go 7.8 standard errors to hit a slope of 0. And so the probability of that happening is like 3 in 10 million. Okay, so 3 out of 10 million times, the slope would actually be 0. So in this particular case, it's saying, okay, I'm like super, super confident that the slope of x to y is not 0. That's what these little stars here mean. Okay, any questions about that? Okay, so this is what the significance codes mean. So this is like 3 stars mean less than 0.1%, I guess. A period for 10%, 1 star for 5%, 2 stars for 1%, 3 stars. Okay, 3 stars for 0.001%. Okay, and the R-squared value is 0.7724. So, 77% of the variation is being captured by this model. Okay. we will talk about what adjusted R-squared means later, so don't worry about that for now. And we'll also talk about what an F statistic is a little bit later on. Okay, so I can go back to my plot here. So let me actually make a new plot. Plot x equals x, y equals y. And AB line of my model dot fit. AB line is a way of adding a line to your plot. A describes your intercept, B describes your slope. If you they have a special thing where you can simply put in the results of your regression into an AB line and it'll give you a best fit line. So let's see what that looks like. So I run my plot again, should be the same thing. And I run my model fits. Actually, I want to do, let's say I want it to be the color red. So it'll look like that. So we can see here, now we are able to plot our line based off of the estimated coefficient against all of the points in the x and y. Okay, so note specifically our, just keep this in your mind right now, our estimate of 0.59 and our standard error of 0.075. What I'm going to do now is I'm going to kind of demonstrate this idea here with these red points. So all we're going to do is we're going to create a new set. Kind of same as before, but now I'm going to multiply my epsilon by 2 so that the perturbation of my points goes farther away. Is that yes? Yes. Yeah, I don't even remember how to do that in the based R. But if we get to the plotting portion today, I'll show a better, better way of doing it. Yeah, which is okay. I mean, the thing is, the way that the plotting works is that it should give a similar, it should try and fit all the points into the plot. So it should be the most efficient for whatever is showing up for your particular thing, even if it doesn't match this. Okay, so this guy should look a little bit different. So you can see here that the points should be a little bit more dispersed. Specifically, you should be able to see this in the axes numbers. And so we are going to make a new data frame with this new set of y2 points that I have. Oh, let me actually, sorry, let me name this y2, not y. Create less confusion. Okay, so we're going to run a linear model on this thing where we've kind of dispersed the y's a little bit more. And let's see what this model tells us. Summary example model 2. Oops. Okay. So here we can see that my estimate has changed a little bit. It's farther now from my actual value, but then so has the standard error. This is doubled, right? Before it was like 0.07 something, and now it's 0.15. So that's kind of what we're seeing in this plot here, right? Where you have dispersed these things out and your standard error is now larger because because the points are more spread out, it's less certain that this is the right slope and that it says, oh, we should like wiggle more, right? Okay, and so we can see what this looks like. I can find my mouse. Here we go. So plot x equals x, y equals y2, and then AB line example dot model 2. Great, and we can see same type of thing as before, but again, the points are a little bit more dispersed, so it kind of makes sense that your standard error would be larger to kind of accommodate the greater uncertainty of the fact that the points are more spread out. Okay, let's see here. So when we looked at actually both of these examples, we note that, hey, the model is estimating this beta value, and it's not quite equal to the beta value. It is within the sort of not that many sort of standard deviations or standard error values, right? So this would be like, we know that this is like 1 and something, some amount of the 0.5, which is the true value, which we happen to know in this case. But it's not super close. So the ability of an estimate for your model to estimate the true value improves when you have more data, right? It's like better able to sort of calibrate to this relationship between X and Y. So in this case, we have like 20 points. So let's say we were to do 1,000,000 points. Yeah, let's just do it like this. We'll do the same thing. Then we'll do a new relationship here, x3 times 0.5. So it's the same equation, but now we have a lot more points. Oops, y3. Okay, so let me run all of these guys. Oops, not deviation, that should be error. So I'm not going to plot this. I would not recommend plotting 1,000,000 points. Oh, this is actually just going to be y. Okay, this will be 4 model.3. Okay, so so even with 1,000,000 points, it runs pretty much instantaneously. So what do you guys think is going to happen here in comparison to what we saw before? More accurate, yes, exactly. So crossing my fingers here. Yeah. So we can see that with a lot more data, my x is 0.498, so much closer to what we know is the true value, 0.5. And then this is 0.0012, much closer to the true value of what we know is 0. Yes. Yes. Yeah. Yep, because of this thing up here. And let me just scroll up just a little bit. Yeah. X3 and error are determined by random draws from uniform distribution and a random draw from a normal distribution. So your computer and my computer are not drawing the same numbers. So yours will be slightly different. Some of you guys will make an estimate that's even closer to 0.5 than me, and some of you guys will maybe make an estimate that's a little bit farther. But your standard errors should be pretty close to mine for both of these. So in this case, we can see now the probability that the model thinks that there isn't a relationship, in other words, that the slope is 0, is 2 in, I don't even know, what's 10 to the 16th, some astronomically small proportion of time that it would be 0. Okay, makes sense, everyone? Yes.
The intercept part,
Mm-hmm.
statistical significance,
Mm-hmm.
can go down.
Yeah. Actually, and we kind of want that to happen, right? Because remember, this is describing how different it is from 0. And it's actually saying only 20% of the time is it would it be 0 or different, or opposite side of the sign. And so it's not statistically significant. And so what the model is essentially saying is that we don't actually think this is like the real number. We think that that the effect is 0, or in this case, the intercept is 0.
So you want that to be a larger number?
No, it's okay. So it's not about wanting these to be large or small, right? We have to like understand what these mean in the context of our model. So traditionally, okay, all this means, all right, on this side, right? This is the probability or sort of the percentage of the time that the effect is 0 or the opposite sign. So in this case, it's saying 20% of the time it's 0 or the opposite sign, right? In the context of what we know about the intercept, we would expect that to be true because we know that the intercept is 0. So I guess in this particular case, for this context, you would want this number to be, I guess, big. Yeah, that's right. Yes.
I guess it went down. That's what
Yeah, okay. So this, yeah, that's an important point, actually. So take a look here. What happens when your sample size increases? What changes in this equation when your sample size increases? Your n. So this gets bigger and bigger. So there is actually this artificial thing that happens. Yeah, this is a common problem actually with big data, which is that as I populate this plot with more and more points, you get more and more certain about the fact that your slope is this value. And that's entirely this artifact of having this n, right? So as n gets big, the numerator gets smaller, right? And so your standard error gets smaller. So all else equal, the more data you add into it, the smaller your standard errors will be. And that's why this value is shrinking over here. That can be a good thing. That can be a bad thing sometimes. Okay. So I am going to do something very quick. Okay, so you guys can't actually follow along here, but that's on purpose. So don't worry. This will all be posted afterwards. There is a famous data set called the Anscombe quartet. I'm going to load this in and we're going to run some regressions on it. Or not, because it's not there. All right, one sec. Oh, it's because I'm probably in the wrong working directory. So this is, right, as I was saying, you have to make sure your workspace is in the right spot where my file that I want to look at is. So I'm going to do that really quick. What, lecture 4? And yes, it's there. Okay. So set as working directory. All right, let's try that again. Okay. So, okay, as I was saying, there is a kind of well-known data set called the Anscombe quartet. And let's take a look at this. So I'm not going to show you the data yet, but I want us to diagnose these models on the basis of, oops, things that we've talked about already. Okay. Volunteer. Voluntold. Can you maybe just walk us through some of the things that we've talked about so far?
Okay, so intercept
3, great.
um,
Okay, okay, standard error of 1. Well, okay, so the intercept hits at 3. How confident are you about the intercept hitting at 3? Pretty confident, somewhat confident, like medium. Okay, so this is saying, right, 2.5% of the time that intercept would go down to 0. So 97.5% of the time, it's like this positive intercepts. So pretty reasonable. Okay, here, slope of 0.5. Yeah, and then you can also judge, right, on the R-squared, it's capturing 0.660. So like just kind of holistically kind of considering the statistical significance of these guys and the R-squared, like what do you think about this model? Is it good? Is it bad? Is it doing a really poor job of estimating? Like, what are your thoughts about this?
I'd say it's not normal, but
Okay. Okay. And maybe that's like you're saying this is like not that close to 1. Okay. All right. Yes.
So when you're talking about like this probability function,
Yes. Over here?
yeah.
Yeah.
Are we going to consider that value or the significance level? Because as per significance level, it's like 90.
Yeah. No, that's the same thing. Okay, so this is 0.002, so that's 2%. So it's actually, so this is saying it's at least, so here, it's at least, it's statistical significant to the 1% level. So it's at least that. It's actually to the 99.8%, right? Because this is, 1 minus this, yeah. Okay. So I'm voluntolding you to help me gauge this next one, okay? Since this isn't punishment for asking a question though. Okay, so summary model 2. So we just looked at model 1. Here's model 2. What do you think? Yeah, okay. They look pretty similar, right? So yeah. So you also think, yeah, decent model-ish, something, right? Okay. What about model 3? Maybe you guys can see where this is going. Summary model 3. Okay. Also pretty close. 3.5 R squared of 0.67. Okay. And lastly, model 4. Basically the same. Okay, so this goes back to what I was trying to say about judging the quality of the model based off of these metrics that we're talking about, your R squared, your standard errors, your statistical significance, right? These are the most common things that people point to when they say, oh, they oftentimes proxy this as kind of the sort of how good your model is. So let's take a look. I'm gonna make this a little bit bigger so that the plot can be a little bit bigger. Okay. All right. So again, this is all gonna get posted online, so don't worry about that. So this is my lesson number 1, is that don't blindly run a bunch of regression models. You need to actually look at the data. So these are my 4 regressions. And they're all telling you the same thing according to my beta coefficients, and my standard errors, and my R squared. Okay. So this is maybe what folks kind of are expecting, right? But you can see that you can also have the same results if you do something like this. Okay, so who thinks this is a good fit for these points? Yeah, pretty good. Who thinks this is a good fit for these points? No? How about this one? Maybe? Yeah, so this is like quite different, right? You've got this like very straight set of points and an outlier. We'll think about ways to handle this. And then how about for this one? Pretty good, right? Yeah. I mean, sure, like, right? Like, so not making any sort of judgments about, without making judgments about this, right? We're talking about, as I was saying at the beginning of the class, you make some assumptions about how your model will sort of fit and describe the relationship between the data. So strictly speaking, like, we're assuming these sort of linear fits here, and maybe that's good, maybe that's bad. And we will consider like, okay, maybe I want to do something different here. Maybe I want to do something different here. Maybe I want to do something different here. But you won't know that, right, unless you look at the data rather than just kind of just run regressions. And so hopefully this will kind of put into your minds that the end all be all of a lot of these regressions isn't just kind of looking at the numbers. We have to do a whole bunch of things to help sort of diagnose whether we think the model is good or not. And part of that is looking at the standard errors and looking at the R-squared, but part of that is also just like looking at the data, right? Because we can intuitively say whether or not things make sense, and if we want to go in certain directions, like saying it's a linear fit versus not. Okay, great. Any questions about that? No, we'll look, and right, I kind of, it's harder than I'm making it seem to be, where you could just say plot the X and the Y, like what if you have a lot more points? What if you're working in more than 2 dimensions, right? So what I'm trying to do in this class is to go through all of the tools that you can, that are available to you that let you do diagnostics, even beyond kind of visualization, although visualization itself can be one of the most important tools. Okay. So we have a little bit of time here. So what I will actually like to do let's talk about doing visualizations in R. So coding and all of that can be somewhat overwhelming, including making plots and visualizations. So I want to maybe try and break it down a little bit. So one, understand the data. To envision desired plot or graph, and maybe that means sort of drawing it out first. 3, manipulate data for plotting. And then it's not until step 4 where we actually do the coding, code the visualization. Okay. So yeah, especially if you are kind of newer to coding, this step might be trickier, right? Because you're trying to figure out how to actually get what you want out of the code into your sort of plot or visualization. But if you are mixing these 3 into step 4 at the same time, it's going to get extra confusing. Okay, so understanding the data first is going to help you kind of decipher what it is that you want out of it, and then envisioning the desired plot or graph. This is going to make sure that you're not kind of bungling around, just kind of putting in code and seeing what comes out. This step, you should really be even sort of drawing like what you think the plot should look like ahead of time, which will help with these 2 steps, right? Because if I know, okay, this is what I want for my X, this is what I want for my Y axes, then I can think about how I might arrange the data to do so. And you've taken care of all of that, and now all you have to do is just code out what you want, and not trying to deal with all of these things simultaneously. So this is I think this breakdown is particularly useful to get at exactly what it is that you want. Okay, so I hate the base R plotting thing. It's terrible. And so what I'm going to recommend everyone do is use a package called ggplot. So ggplot2. And I'm going to kind of break down the components of this, and I'll also post some tutorials on this package as well. So there are a whole bunch of if you kind of just dive right into it, there's a whole bunch of things that might be really confusing, but I'm going to try and break that down. Okay, so the components of it are something like, so you've got ggplot here. And the two main things that go here are data and AES, and okay, I'm going to show what this is in a second. We have geom. Okay, and so this is what you put to decide whether or not you want like a line graph, a point graph, a bar graph, and so on and so forth. There's a ton of options here. And then everything else is all about tidying up the plot. Okay, and so what are my options here? So these will be things like axis names, axis cutoff, chart name. There are themes you can do here. If you want to mess with the legends. And then there's one more thing that I'm actually going to put separate. So this isn't part of the tidying. There is facets, which is helping to do grouping operations. Okay. So I'm kind of going to freehand some of this. All right, so give me one moment. So I think what I'm going to do is load in the data from before. About that coronavirus data sets. So this part, I'm going to say you don't necessarily have to follow along. Again, I'll post all of this on Canvas. But what I'm going to ask for us to do, what the heck is this? All right, well, hopefully this still works. What I'm going to try and do is to have us think about visualizations we want to do, walk us through some of these steps, and then I'll show some examples here. So let me load in this data, which, all right, one sec. I'm just going to pull in some code that we did from before. And I'll walk through it really quickly. Okay, actually, sorry. We don't have that much time left. Okay, I just realized there's something else that we have to cover that's relevant for the homeworks. So, okay, I'm gonna hold off on this stuff and we will go over it next class, next week. But actually what I wanted to show is about R Markdown. So all the homeworks have to be done in R Markdown, which is let me just show you here. So this will get posted. It's kind of a meta document. Here we go. So let me blow this up quite a bit. Sorry, I'm jumping around here. One moment. Okay. So this is an R Markdown file, which is different from a .r. It's .rmd. And what is R Markdown? This is a file type that allows you to both save and execute code while generating reports in formats like HTML or PDF. And so homeworks need to be submitted in this format. And you can submit both the RMD file and the HTML PDF file. This way, our grader can actually run your code and check things themselves to see everything is working. You've got 3 different types of content. So I should also just say that like I don't use R Markdown. I've never used it prior to making this document, but it's actually pretty straightforward and easy, so it should be easy to learn. There's 3 types of content. The first one is up here, where you have this separated by these 3 dashes. This is known as YAML metadata. And so this lets you do things like set the title, what the output file should be, and you can have some themes about like colors and fonts and that sort of thing. So that's the first one. Everything else is kind of as a text just here. So you can kind of see in this like meta documents what it looks like. And I kind of describe some formatting things. So like if you have these pound symbols, these do things like make them as headers or really big headers or small headers. And that's all part of the chunk of stuff that's in your text. And then you can see some options for doing like italics and bold and that sort of thing. So for folks who have ever used LaTeX, you can actually make equations in R Markdown in the same way. So that's these dollar symbols. And then code chunks. So code chunks are done in this way. You have 3 consecutive backticks, and then the chunks are ended by backticks as well. So that looks something like this here. So this is a code chunk. So I have tick, 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 squiggly thing R, and then tick, tick, tick at the end. And there's options about what gets printed into your documents here. And so I talk about that up here. So you can have include equals false or echo equals false. And so I have the 3 settings here, my default setting, my echo to false, include to false, and so on. So let's take a look at what happens if I run this. So you need to hit this button here called knit, and that's the thing that compiles your R Markdown file. So if I click this, it's going to run through all of it, and then it can actually, even though this is like a document that's getting made, it can actually run and execute code in these code chunks that are being specified. And I do have one example of a plot in here. So this is compiling. Okay. And here you can see the sort of final document. And so it's just the same text that we saw before. Now everything is formatted, right? You can see, the examples I was saying of how to make italics or bold, the equation that I was saying. Okay, and then in the code chunks, right, what gets displayed out of this print hello and so on, right? You can see here, you have in the default, it shows everything. Setting echo to false, it only shows the things that get printed. And setting include to false, nothing ends up getting shown. Okay, so again, I'm going to post the R Markdown documents and the compiled documents into Canvas, so you guys can have a look at how to make those. I think it's pretty straightforward. But if anyone has any questions, you can ask me or Vaish. Okay, so that is all for today. Hopefully folks will start looking at the homeworks, which will be due 1 week from today on the end of Thursday. Yes.
Do you want us to echo the code, or like it echoes false?
Up to you. Up to you.
Fantastic. That's my favorite answer.